Welcome to a deep dive that I think you'll find particularly fascinating. It's a research paper that reveals a surprising connection between two seemingly disparate fields, neural networks and differential equations.
We'll be exploring the work of Maria, Laura Piscopo, Michael Spanowski, and Philip Waite from Durham University.
They've proposed a novel method for solving these fundamental equations using AI.
Their paper titled Solving Differential Equations with Neural Networks, Applications to the Calculation of Cosmological Phase Transitions, explores how neural networks, typically known for pattern recognition, can be harnessed to tackle complex mathematical problems that are crucial for understanding the universe.
This approach is particularly intriguing because it offers a potential solution to a long-standing challenge in physics and mathematics.
Finding accurate and efficient ways to solve differential equations which describe how systems change over time or space.
The core idea lies in reframing the problem of solving differential equations as an optimization task.
Neural networks excel at optimization, finding the best set of parameters to achieve a desired outcome.
So by carefully crafting a loss function that incorporates the differential equation and its boundary conditions.
The neural network can be trained to approximate this solution.
This differs from traditional methods that often rely on trial solutions or complex numerical techniques.
By incorporating boundary conditions directly into the loss function, the neural network approach offers greater flexibility and stability, potentially leading to more accurate and efficient solutions.
The paper demonstrates the versatility of this method by applying it to a variety of differential equations, starting with ordinary differential equations of both first and second order.
These examples serve as a validation, showing that the neural network can accurately reproduce known analytic solutions.
The researchers then move on to more complex scenarios, tackling coupled differential equations, where the solutions of two equations are interdependent.
This highlights the iterative training process used to ensure the stability of the neural network solution over larger domains.
The paper also demonstrates the applicability of this method to partial differential equations, which involve multiple variables and are common in fields like fluid dynamics and quantum mechanics.
This broad applicability hints at the potential of this approach to revolutionize how we solve complex problems in various scientific disciplines.
One of the most exciting applications explored in the paper is the calculation of cosmological phase transitions, crucial events in the early universe that might hold clues to the origin of matter and the existence of gravitational waves.
These phase transitions are thought to have occurred as the universe cooled, leading to significant changes in the fundamental forces and the formation of particles.
A key concept in understanding these transitions is the bounce solution, which represents the most probable path for a phase transition to occur.
This solution can be found by minimizing the Euclidean action, a mathematical quantity that describes the system's evolution.
However, the equation that governs this bounce solution, often a set of coupled nonlinear differential equations, can be notoriously challenging to solve using traditional methods.
The authors of the paper directly compare their neural network approach to two established solvers, specifically designed for calculating phase transitions: Cosmotransitions and Bubble Profiler.
They analyze three specific examples, each highlighting the strengths and limitations of the different methods.
The first example involves a single scalar field and focuses on the difference between thick wall and thin wall transitions.
This distinction relates to the shape of the potential energy landscape and affects the profile of the bubble that forms during the transition.
In essence, the wall refers to the boundary between the old and new phases, and its thickness is determined by how abruptly the transition occurs.
In the case of a thick wall transition where the change is gradual, all three methods, the neural network, Cosmotransitions, and Bubble Profiler, agree on the solution.
However, discrepancies arise in the thin wall scenario where the transition is more abrupt.
Interestingly, both the neural network and Bubble Profiler correctly predict the bubble radius, a crucial parameter in the thin wall case, while Cosmotransitions deviates from the expected value.
The second example increases the complexity by considering a system with two scalar fields.
This scenario is more challenging because it involves visualizing the path that these fields take during the transition.
Here again, the neural network and Bubble Profiler demonstrate close agreement both in terms of individual field profiles and the overall path taken by the fields during the transition.
The results, however, contrast with those obtained using Cosmotransitions.
The final example tackles a more realistic and complex scenario: the singlet scalar extended standard model, a popular extension of the standard model of particle physics.
This model introduces a new particle, the singlet scalar, which could potentially explain dark matter and the origin of matter.
This example also incorporates the effects of finite temperature, making it a more challenging calculation.
Remarkably, all three methods, the neural network cosmotransitions and bubble profiler, show very good agreement in this case.
One of the notable features of the neural network approach is the use of what the researchers call f-hat.
This quantity measures how well the neural network's solution satisfies the differential equation at each point in the domain.
F-hat essentially acts as a built-in accuracy check, allowing researchers to assess the reliability of the solution even without knowing the exact analytical form.
This is particularly valuable when dealing with complex problems where analytical solutions are elusive or impossible to obtain.
The ability to assess the accuracy of the solution without relying on an analytical benchmark is a significant advantage of the neural network approach. It provides a level of confidence in the results, especially when dealing with complex systems where traditional methods might struggle to provide reliable solutions. The implications of this research extend far beyond the specific examples presented in the paper. It suggests that neural networks could become powerful tools for solving a wide range of problems in physics and other scientific fields.
The authors emphasize that this approach is not limited to differential equations arising from physics. Any problem that can be framed as finding the zeros of a function, a common task in many scientific and engineering disciplines, could potentially be tackled using this method.
This opens up a vast array of possibilities.
Imagine using neural networks to model complex systems in fields like fluid dynamics, materials science, or even finance. The potential for innovation is immense.
The paper briefly touches upon the broader implications of using neural networks to solve differential equations, particularly in the context of quantum field theory. This is a realm where analytical solutions are often unattainable, and numerical methods can be computationally expensive.
Quantum field theory is the foundation of our understanding of particle physics and the fundamental forces of nature. Being able to solve the complex equations that govern these theories could lead to breakthroughs in our understanding of the universe at its most fundamental level.
The authors leave us with a thought-provoking question. If neural networks can effectively tackle differential equations, what other seemingly intractable problems might they help us unravel?
This question highlights the transformative potential of artificial intelligence in scientific discovery. As neural networks continue to evolve and improve, they could become indispensable tools for researchers across various disciplines, enabling them to tackle problems that have long defied traditional approaches.
The paper we've explored today underscores the power of cross-disciplinary thinking. By bringing together concepts from computer science and physics, the researchers have opened up new avenues for scientific exploration.
This fusion of disciplines is becoming increasingly important as we grapple with complex challenges that require innovative solutions. The ability of neural networks to learn and adapt makes them particularly well suited for tackling problems that are difficult or impossible to solve using traditional methods.
This deep dive has provided a glimpse into a future where the boundaries between seemingly disparate fields blur, and artificial intelligence plays a central role in advancing our understanding of the universe.
The progress made so far in using neural networks to solve differential equations is remarkable. However, challenges remain.
Researchers need to develop robust methods for choosing optimal network architectures, determining appropriate training domains, and ensuring the stability and reliability of the solutions.
Addressing these challenges will be crucial for realizing the full potential of this approach and transforming it into a reliable and widely adopted tool for scientific discovery.
The paper we've discussed today is just the beginning. As research in this area continues, we can expect to see even more innovative applications of neural networks to solve complex problems in physics, mathematics, and other scientific disciplines.
It's fascinating to consider the potential of neural networks to completely change scientific research.
Their ability to handle complex nonlinear equations and adapt to diverse boundary conditions, it makes them uniquely suited for problems that have long challenged traditional approaches.
Instead of grappling with tedious numerical methods, imagine a world where researchers can train a neural network to find solutions with remarkable accuracy and speed.
This could accelerate breakthroughs in our understanding of fundamental phenomena.
From the behavior of subatomic particles to the evolution of the cosmos.
While there are challenges to overcome before neural networks become the standard tool for solving differential equations, the progress made so far is undeniable.
The development of robust methods for choosing optimal network architectures, determining appropriate training domains,
And ensuring the stability and reliability of the solutions are all areas of active research.
This deep dive has provided a glimpse into a future where neural networks become indispensable tools for physicists, mathematicians, and scientists across various disciplines.
The paper's exploration of using neural networks to solve differential equations really opens up a world of possibilities for scientific discovery.
It's an invitation to consider the vast potential of artificial intelligence to unravel the mysteries of the universe and drive progress in fields we haven't even imagined yet. Well, that wraps up our deep dive into this remarkable research paper. I hope you found it as thought-provoking as I did.
It's certainly an exciting time to be witnessing the convergence of artificial intelligence and fundamental science. Who knows what breakthroughs await us in the years to come?
Sus.